Okay, year 11, again no picture because you won't be able to see the slides, but we're going to go through the second part of the paper. Most of the calculations are in this bit, so if you need to replay any part of it, then by all means stop the video and have another go at any particular question as we go. Right, so starting with question 7 then. Notice we have an energy profile, energy level diagram. You want to try and interpret this before you go any further. So look at the reactants on the left hand side at the lowest energy, then the products on the right hand side at a higher level of energy. Interestingly, that means that the energy change you can see is taking in energy, so the overall energy change is moving upwards. The activation energy they're labeling as the bump, okay, but where does that bump start from? They're starting it from the products level. So there's all sorts of things on here that we need to consider. Okay, errors made therefore on that reaction profile. Firstly, the activation energy should be from the level of the reactants to the top of the bump. That's the total amount of energy that needs to be taken in order for the reaction to start. We usually associate that with breaking bonds. Secondly, we need to think about this exothermic reaction. Production of water is an exothermic reaction. In fact, if you put hydrogen gas and oxygen gas together, you get an explosion. Think about the Hindenburg disaster when they had the explosion of the air balloon. Okay, so really we should have the products at a lower level, like you can see on my second picture here, and therefore the energy given out, you can see my arrow pointing downwards on the green arrow on the right hand side. Okay, so activation energy should be from the reactants to the top of the bump, and because the reaction is exothermic, we can see that the reactant energy should be above and the product energy should be below at a lower level. Okay, so this time reaction between hydrogen and oxygen in a hydrogen fuel cell is used to produce electricity. Okay, so there are some rechargeable cells now. Two advantages of using hydrogen fuel cell instead of rechargeable cells to power cars. Okay, first of all, it is a quick process. Recharging the cell is a quick process. It doesn't produce the polluting carbon dioxide that we need to consider. So it's a clean process. And though rechargeable batteries can be recharged over time, they do gradually degrade and not recharge as well, as we're well aware of with our phones, etc. And therefore it's not as effective a process as time goes on. Reactions occurring at the positive electrode and at the negative electrode in a hydrogen fuel cell, you need to choose one or the other. Okay, so we can choose either at the positive or at the negative. So at the anode we see oxidation, at the cathode we see reduction. If we have an acid electrolyte, this is what we'd see, those funny little question marks are the arrow for the reaction. We could also have, if we had an alkaline electrolyte, which is the second possibility for our fuel cell. Notice this time round we're using alkali rather than acid and producing water. So here's our two reactions this time. Overall, you can see the process is exactly the same. Okay, part 4 then, states of matter. What have we got in front of us? A box with some dots in it. What are the limitations of this process? Okay, so it's only giving you a 2D representation. It's not showing you what's happening in 3 dimensions, and obviously the gas particle movement is in 3 dimensions. It's not showing you that we've got 2 atoms joined together in a diatomic molecule. It's just showing a single splodge. Doesn't give you any indication of the movement of the particles, so you can't see them moving in any way, shape or form. Remember, I often draw little cup shapes behind them to indicate that they're moving, but even that is not a really accurate. And it's not showing that there are any intermolecular forces between our hydrogen gas molecules, which clearly, though they're weak, there still are. So any 2 limitations, any 2 of those to get your 2 marks. This is just a diagram that we hope might help you thinking about the good things and the limitations of the different representations, the way we show our molecules. So it's worth having this idea and being aware of this idea of a Lewis structure showing the pairs of electrons in our shared covalent bonds on the far right hand side. Part 5, hydrogen gas is needed to power a car for 400 kilometres, would take up a large volume. How could we reduce that volume? So how can we reduce the volume of a gas? Remember, the particles are far apart, so we can either increase the pressure on it in order to push the particles close together, or you could say just scoring it as a liquid as being what happens when we increase the pressure as eventuality anyway. Okay. There is this third method about absorbing it onto the surface of another chemical, but I wouldn't expect you necessarily to be familiar with that one, and the first two are far more common sense answers. Okay, our first calculation, and remember we've said this before, for a calculation question you can score all the marks for getting the answer right, but if you don't show your steps in your calculation, then you make a mistake, then you'll lose all 4. Okay, so first of all, it's talking about megajoules. Convert your megajoules to kilojoules so that we're using the same unit throughout. Then we need to work out the number of moles of hydrogen which are being generated, and then convert from moles into a volume of gas. Okay, so 58 megajoules is 58,000 kilojoules. From the question, it tells you that 290 kilojoules is what's produced when we have 1 mole of hydrogen gas. So we have 200 moles of hydrogen gas here, 58,000 divided by 290. If we've got 200 moles of gas, we know that 1 mole of gas is 24 litres or 24 decimeters cubed. So we simply need to multiply our 24 by 200 to get 4,800 decimeters cubed. Okay, so question 8. Now we have to remember our information we know about group 7, the halogens. They're giving you information at the start here about the melting and boiling point of the different halogens. So we need to remember what we mean by melting point and boiling point. Okay, so before it melts it's a solid, after it's melted it's liquid, after it's boiled it'll turn into a gas. So our question is now, if it was 0 degrees, since it melts at -7, what state will it be by 0? It will have melted and therefore it will have turned into a liquid. When we get to 100 degrees C, it will have boiled, so it will have turned into a gas. Hence our answer to our question is going to be that it's turned into a liquid before 0 and it's turned into a gas by the time we get to 100. Now explaining our trend in the boiling point. So if you look at our boiling points, the trend as we go down the group is that our boiling points are getting higher. So from -188 up to 59. That's just a statement. Now we need to explain that. Okay, so as we go from our small fluorine to our much larger bromine, the mass of the elements is going to increase, which means that the forces, the intermolecular forces, are going to be stronger. Therefore, it's going to take more energy to overcome those intermolecular forces and push our atoms apart, and hence we're going to see a much higher boiling point as those forces become stronger. Why isn't it correct to talk about the boiling point of a single bromine molecule at 59 degrees? Okay, if you think about it, when we're talking about boiling point, we're talking about the particles moving apart. If you've only got one molecule, what's it moving apart from? Okay, so you can't talk about the state of matter of a single molecule. It will always be effectively a gas because it's got nothing else around it. Okay, so if you've only got one molecule, you can't talk about it having a state of matter. Okay. Now this is a classic experiment, not one that we do very willingly, because obviously we've got to generate our halogen and we've got to find a way of getting rid of the excess halogen, and since we know about the toxicity of our halogens, it's not something we would often do except in a fume cupboard if we needed to. purely and simply because of the toxic nature of those gases. Okay, so the halogens are toxic, therefore if you were to do it, you would need to do it in a fume hood for safety. And question 8.5, now this is a very, very common question. Note it's asking you to explain, and we're talking about why the reactivity decreases as we go down the group. So looking at those atoms as we go from fluorine down to iodine, the atoms are getting larger, and what we're trying to do is to pull in an extra electron to complete the outermost shell. What is it that pulls in that outer electron? It's going to be the attraction between the outer electron and the positive nucleus. So the further away the outer shell is from the nucleus, the weaker that pull is going to be, and the greater number of shells between the nucleus and our outer shell, that's going to shield the positive nuclear charge from the outermost electron, and again it's going to weaken that force of attraction. Okay, so as we go down the group, the number of shells is increasing, so there's going to be more shielding. The size of the atom is going to be getting larger, therefore the attraction towards the nucleus is reduced. Hence, gaining that outermost electron is going to become less easy, and hence reducing the reactivity. You must talk about the size of the atom, and you must talk about the shielding effect of the layers, the other shells in between, in order to get your marks, and talk about that outer shell being pulled in by the attraction, the electrostatic attraction between the electron and the nucleus. So a little bit of practical science now, showing you a reaction, iron reacting with chlorine using the equipment that we had at the beginning of the question. Calculate the simplest number ratio between the number of iron atoms and the number of chlorine atoms in order to generate our balanced equation. So what do we need to do? So first of all, we've got to work out how much iron we had, which was obviously our starting point, taking away the mass of the original tube. Then we need to work out how much iron chloride, and from that how much chlorine we have. We could do that second one by taking the difference between the iron chloride and the iron, and you would end up with the same number. Okay, now we have masses of iron and chlorine. We don't need masses, we need to convert those into moles, so we divide the mass of iron by the relative atomic mass of iron, and we divide the mass of chlorine by the relative atomic mass of chlorine. Notice the relationship between those two, so we look at our ratio and convert that into its simplest form by dividing through by the smallest number, and therefore we get our simplest ratio of 1 to 3. So for every 1 iron we will have 3 chlorine atoms, and hence we can work out our balance of our equation, remembering that our equation has to have chlorine molecules. Therefore we need to double up 2 ions to 3 chlorine molecules, 1, so that's 2 to 6, 1 to 3, allowing for chlorine being Cl2 for our final mark. Okay, question 9. We have the information about our reaction, how it was carried out. So mixing our sodium hydrogen carbonate in a polystyrene cup with our citric acid, taking the starting temperature of the solution and then measuring the final temperature, and then repeating our steps with increasing quantities of citric acid each time. This, as you probably remember, or I hope you remember, is one of our RPA formats. Here is the results which have been drawn for you, and also they've drawn your line of best fit for you. Notice it's an endothermic process because it's taking in energy. The temperature is going down as we have more of our acid available. We can see the lowest level, the lowest temperature reached at 1.5 grams of citric acid. And we can see that after that 1.5 grams of citric acid, we're then seeing the temperature rise again because there's no more reaction taking place, and therefore it's going to move back up towards room temperature. Okay, so we have one anomaly, the one point that didn't fit on the line. Why might that anomaly have happened? Simplest answer, if they didn't stir the mixture, then that temperature would have been higher than expected because only some parts of the liquid will have been cooled. So the simplest answer is that they didn't stir the mixture. Explain the shape of the graph in terms of the energy transfers taking place using data. So you need to refer to that data. So as you saw me do on the previous slide, in the first experiments we saw adding extra citric acid meant the temperature went down because we were breaking more bonds as we added the acid. So it's transferring energy from the surroundings into our reaction, hence the temperature goes down. Once it's all used up, then by 1.5 no further change in temperature going down takes place, and therefore energy is going to be transferred back to the beaker and the temperature will come back up from the surroundings. Right, you must refer to the data. Second part. We're going to repeat the experiment now using a metal container instead of the insulated polystyrene cup. What would you expect that to do, given that you've got the same size and shape, so the only thing you're changing is the conductivity of our metal compared with the insulating properties of our polystyrene cup. Okay, so that thermal transfer process, bringing in the heat from the surroundings, is going to happen quicker. So the temperature decrease is not going to be as great because it's going to bring in energy from the outside quicker, and therefore bring the temperature back up. So what you'd see as it absorbs that is we'll see an increase in the level of the line at a higher level than it was before. Okay, so we'd see our line at a higher level. Not necessarily going through the anomaly, that's purely by accident really. Okay, calculation again. So we've got 250 centimeters cubed of solution with a concentration of 0.05 moles per decimeter cubed. So there's our starting point, and like we've always said before, check your units. Centimeters cubed compared to moles per decimeter cubed, so we need to correct that first of all. So we need to divide by 1,000. So erosive formula mass of our substance, we add together 6 lots of 12, 8 lots of 1 and 7 lots of 16 gets us to 192. Concentration 0.05 and volume 0.25. Therefore we've got 0.0125 moles of our citric acid. We want to know the mass of citric acid, so we're going to multiply that by 192 to get 2.40 grams. That's our final answer. And then our favourite, titration experiments. Go through the steps. How would they complete the titration? So you take your starting reading on the burette, whatever that might be. You add your citric acid solution to it drop by drop until we get our colour change on our indicator, making sure that we've mixed it steadily along the way. When the colour change takes place, we take our final reading on the burette in order to work out the total volume that's been added. Going into a little bit more detail, if we're thinking about the whole way of describing the process of the titration, We use a pipette to measure the fixed volume of one liquid. We put that into our conical flask and add our indicator to it. We fill the burette with our second solution, in this case the alkali. Take your readings, add your solution from the burette until you see your change into your indicator, making sure that you mix along the way, and then find out what our final reading when we reach our neutral point. Why do we use a burette for the citric acid solution? Remember, the citric acid, we're adding little by little into our mixture. Right, so we're adding varying amounts from our burette, but we're doing it with a precise measurement. And how do we do our calculation? So for the acid, what information do we have? We know we have a volume converted into decimeters cubed. We know we have a concentration already in decimeters cubed. Therefore, we can work out the number of moles of citric acid present. For our alkali, we know the volume. From our equation, we know that we need 3 times as many moles of our alkali NaOH as we have of our citric acid. Since we know the number of moles of acid, we can work out the number of moles of alkali required by multiplying by 3. Now I have a volume and I have a number of moles, so I can work out the concentration for my alkali, dividing the number of moles by the volume to therefore produce my concentration of 0.0798 moles per decimeter cubed.